Welcome to the last talk. Before I hand over the microphone to the chairperson of the talk to introduce the speaker, I'll just take 2 minutes of your time to say thank you to the people involved. So this is a vote of thanks for this program. So funding and patronage, so this is funded entirely by the Institute of Mathematical Sciences. Thanks to Professor R. Balasubramanian, the director, whom you saw yesterday. He was the chair of the first session. So thanks to him for the funding and the patronage. Thanks to all the speakers and the chairpersons and to the IMSC faculty who've suggested the names of speakers and helped me organize this program. Administration, our registrar, Sri Vishnu Prasad, is a great help. He's not around, unfortunately, but they're always ready to give us full support for any initiative that we take, so that we can take these initiatives without fear of just worrying about the academics, not worrying about the administration, which is a great thing. In particular, Miss Indra, whom you might have seen, she's in charge of this program, and Sri Parthiban, these are administrative officers at the IMSC office. Thanks to them, they've been assisted by many administrative trainees whose names I'm not mentioning here, but thanks to all of them. So I should mention certain names. The online registration was Sri Ravindra Reddy, who's a systems administrator here. He helped me set it up. Thanks to him. The poster was designed by Ms. TV Haripriya, who's an administrative assistant here. The notebook design and printing was done by Sri Johnson of the IMSC office. And for technical help, I thank G.S. Vasan, whom you've seen around, and many others who will remain nameless, unfortunately, but thanks to all of them. Please do give them a big hand. And the catering is by V. Sundarlingam and Company. I hope you enjoyed the food, and particular thanks to the catering personnel who serve with a smile. So please do give them a big hand. I'm really thankful to them. So videos, slides, and notes. So videos and slides of this workshop will be available on the web page of the workshop. The web page of the workshop, or I should have said program, will be permanently, it's the same. I mean, hopefully it will be, like I said, freely, happily, forever after. Yeah. Many more videos are available on the Mad Science YouTube channel. And this program is planned to be an annual affair. So it is the third year that this program is running, maybe with just a little, it's not with the same title, but with just slightly modified titles. And it is planned to be an annual affair. So look out for an announcement next year around the same time if you're interested. Okay. We value your feedback. So do send them by email to me at, that's my address, which you know already. So that's it for the vote of thanks, and it's a pleasure now to invite my colleague, Professor V.S. Sundar, to chair this last talk, which is by Professor S. Sundar.
To introduce our next speaker, Sundar is a 100% Tamil Nadu product. Like Vishwanath. Vishwanath was slightly tainted by, like Venkatesh, although Venkatesh was slightly tainted by a visit to TIFR. Sundar is entirely Tamil Nadu. So he did his bachelor's in VOC College in Tuticorin, and then he came to IMSC after his BSc to join this what we call an integrated PhD program. And in his first 2 years, I saw quite a bit of him. I taught him a course in measure theory, I think, and then he wrote a master's thesis with me, and then he went on to do his PhD with my colleague Pathasarathi Chakrabarti, and already he's made a mark for himself. His name is known to all the experts in the area. He works in this relatively young area of mathematics called non-commutative geometry, and I would like to take some pride in the fact that I may have had something to do with influencing him to work in this area of mathematics, and he will be talking to us on what could be called a baby class version of non-commutative topology. So, Sundar.
So, yeah, thanks. So this will be a 75-minute lecture on linear algebra. So I hope that will motivate you. So I work in a field which, as Sundar has said, I also work in operator algebras. So the kind of objects that we study in operator algebras are, I'll define properly. So the kind of objects that one studies in operator algebra is H will be a, don't worry if you don't understand the thing. So if H is a Hilbert space and BH is the space of bounded linear operators on H, and A will be subalgebras of it. So, but I'm only going to assume everything to be finite dimensional. So I hope everybody has done a course in linear algebra, right? So how many of you are in BSc? Can you just, okay, so have you seen linear algebra? Yes? Okay, so I can assume you know what is a vector space. Do you know what is an inner product space? Okay, so I will assume that everybody knows, everybody has seen an inner product space. So and then we'll build on that. Okay, so for this talk, H will be a finite dimensional inner product space. So if you, H will be a finite dimensional inner product space over C. You can assume it's over R also, but I will assume it's C because I would want linear operators on H to have eigenvalues. Okay, so example, the only example is this. As you know, any finite dimensional space is isomorphic to Cn, and it's an inner product space. And what's the inner product here? The inner product here is the inner product is defined like this, and so on. So an inner product is, as you know, it's just a pairing between two vectors where it's linear in the first variable, antilinear in the second variable, and you have the positivity and positive definiteness and so on. Okay? Okay. I mean, I'm not listing out all the axioms of an inner product space, I'm just saying. So H will be a finite dimensional inner product space over C. So you can assume H to be Cn if you prefer. And look at all bounded all linear maps from H to H. So BH for us will be all linear maps from H to H. Okay, okay. So if H is Cn, then BH is nothing but matrices. In an inner product space, you always have what is called the adjoint of an operator. The adjoint of an operator is defined like this. That is, if T is an operator, the adjoint of T is defined by the equation so that means that if you have an operator, there is an adjoint T star for which this equation makes sense for every psi and eta. So the bounded linear operators, first of all, it's a vector space. You can add them. You can add two linear operators and you will still get a linear operator. You can multiply them. What I mean is composition. And you also have an adjoint operation. And what are the properties of this adjoint operation with respect to the multiplication and addition? It's conjugate linear. And it is anti-multiplicative. And it's involutive, which means that if you take the adjoint of an adjoint, it's equal to the same thing. So if you have a finite dimensional inner product space, the algebra of operators on H has an adjoint operation for which these things are satisfied. And this is the canonical example of the kind of objects that one studies in operator algebras. So in the case of M and C, what is the adjoint? If you take a matrix, its adjoint. So if A is Aij, the adjoint matrix is given by the ijth entry of A star is Aj bar. So you take the transpose and take the complex conjugate, that is the adjoint. So you can verify that if you define the adjoint like this, it will satisfy these properties. Okay, so the canonical, the first example of star algebra, as what I call, is, so look at BH. So it is the linear operators on H. This is the canonical example of a star algebra. So this is first of all a vector space, or you prefer it's M and C. It's either M and C or BH. So it's a vector space first of all, and it has multiplication. And it has a star structure. Okay, there are three structures. A vector space has addition and scalar multiplication. So there are four structures as of now. This, you can add two matrices, you can multiply two matrices, you can multiply a scalar with a matrix, and you can take the adjoint. So there are these four structures and they interact with each other. That is, if you take, that's the interaction is given by those equations. That is, if you add and take the adjoint, it's given by this. If you multiply and take the adjoint, it's given by, it's given it changes the order and so on. Okay, so this is the kind of, this is an example of what we call a C star algebra. Okay, so the objects that one studies in operator algebras is these kind of objects. So what do I mean by these kind of objects is, So, definition, a star algebra A is an algebra. So I am not going to define everything, I am just, it is an algebra with a star structure. So what do I mean by that? You can, it's a vector space first of all, it has a multiplication and it has a star structure. So what's a star structure means? There is a map from A to A such that A plus B star is A star plus B star, AB star is B star A star, and alpha A star is alpha bar A star. So it preserves the addition, but the scalar multiplication, the conjugate will come out and it reverses the order of multiplication. And it's an algebra. It's an algebra means it has addition and multiplication, that's all. So I'm not going to formally define what an algebra is by listing down all the axioms, but and what is an example of a star algebra? The canonical example is the matrix algebra or BH. Okay, but there are other examples too. This is the all the axioms of an involution. Involution I missed out, right? Sorry. It's, if you take the adjoint of the adjoint, it becomes the same thing. Okay? Okay. But there are other examples of star algebras too. So I will list so let's the example first, baby example. So X is a finite set, and look at, or if you want, it's a, okay, it's, I'm only interested in finite dimensional algebra, so I will assume it's a finite set. So X is a finite set. Look at Cx, which is all the functions on X. Okay, so functions on X means functions from X to C, X to complex numbers. If I take two functions f and g, I can add them, f plus g. If I take two functions f and g, I can multiply them, which is fg, pointwise, and I can take the conjugation. So the addition is given by this. The multiplication is given by this, and the star operation is given by the addition is pointwise addition, multiplication is pointwise multiplication, and star operation is taking conjugate. So this is a star algebra with addition being this, multiplication being this, and star operation being this. Okay, okay. This is another canonical example of a star algebra. Okay, let me give me one more example, which is a bit slightly complicated. So, by the way, is this a finite dimensional finite dimensional algebra? What's the dimension of this? Somebody answer, please. What's the dimension of Cx? From the back, not from the first. Cardinality of x, right? So the dimension of Cx is just cardinality of x. So one more example is what is called the group algebra. So let G be a finite group. Okay, I am going to define, I am going to take the same thing, all functions from G to C, okay, and but then if I define the multiplication like that, then it's the same algebra. There is nothing, there is no difference between one and the other, right? But I am going to use the group operation on G to define the multiplicative structure. So this is a finite dimensional vector space. So what is the basis for it? For G in G, let delta G be the indicator function and 0 if x not equal to G. So it is just the indicator function on, it's just 1 if x equals G and 0 if x not equals G. And this forms a basis okay. So this forms a basis for CG. And how do you write an element, how do you write if, so I think I should, how do you write a typical element of F as a linear combination of delta G? So if F is an element in CG, I can write F as summation AG delta G. But what is AG in terms of F? It's just F of G, right? So you can write any element as linear combination of delta G. So, so this forms a basis. So if I give you two elements, F and F1 and F2, you can write it as linear combinations of delta G, and then you are going to multiply F1 and F2. Okay, so you just multiply. I am going to use this as the notation for multiplication. So you just multiply and expand it out. F1 of G, F2 of H, delta G star delta H. So you just multiply it out. And then, so the entire multiplication is determined by what happens on delta G star delta H. Okay, so I define the multiplication such that delta G star delta H is delta GH. So define multiplication so that delta G star delta H is delta GH. Okay, and then and if you do so if you do that, then what is, so if you want it to be more precise, then the multiplication is given by the following formula. So what is F1 star F2 is just summation F1 of G, F2 of H, delta GH. So let me rewrite it. So let me write GH as say S. So this becomes summation of F1G, F2 G inverse S, delta S, G and S. So this is equal to summation S. You just so the value of F1 star F2 at S is given by this formula. If you so if you want it to be more precise, I define the multiplication like this. So this is what is called the convolution of F1 and F2. Okay, so how did I arrive at that formula? I arrived at that formula precisely because I want this equation. So I want, so if I think of delta G as simply the group element, G times H to be GH. So I want that equation. So if you demand that, then the only way you can define multiplication is this, and this is called the convolution of two functions, and with respect to that it becomes an algebra. And what is the star structure? The star structure is, so similarly I demand the star structure to be defined by this equation. So the group algebra is simply, the group algebra simply is just linear combinations of delta G, and if you write one linear combination of delta G, another linear combination of delta H, if you want to know how to multiply them, you only need to know how to multiply delta G and delta H, and that is given by this rule. And if you want to take conjugate, you only need to know how to take the star of delta G, and that is given by the inverse operation. Okay, so with respect to this, the group algebra CG becomes a star algebra. So the CG is a star algebra. So I have given so far 3 examples of star algebras. The first is BH. H is a finite dimensional Hilbert space. And the star structure is the usual adjoint here. The second is functions on X. X is a finite set where the star structure is the complex, the multiplication is pointwise multiplication and the star structure is complex conjugate. And third one is the group algebra. And I just explained how the star structure and multiplication will look like. Okay, so these are, of course, in operator algebras, one studies, one allows things to be infinite. So H will be an infinite dimensional inner product space, and X will be not a finite set but a compact set, and G will be a locally compact group. Okay, so but for this lecture, it's enough to know these 3 examples of star algebras. Okay, and I said that this, so 1 and 2 are considered to be the canonical examples of what is called C-star algebras. I should explain what a C-star algebra is. A C-star algebra is just a subalgebra of BH. So what do I mean by that? So C-star algebra is a star subalgebra of BH. So what do I mean by that? So you have BH. BH is a star algebra. It has a star structure, multiplication, and so on. So you know what it means to study. What do I mean by saying A is a subalgebra? It means that if you take 2 elements here, and if you add them, you still lie in A. And if you take 2 elements A and B in A, if you multiply them, you're still in A. If you take an element, its conjugate is also in A. That is what it means to say it's a star subalgebra. Okay? Okay, and I also assume that it's unital. Unital means the identity matrix. So if the identity matrix or the identity operator is also in the same algebra. Okay, so a C star algebra is nothing but a subalgebra of BH. Okay, and so are these examples of C star algebras? Certainly, BH is a subalgebra of its own. What about CX? Is CX a subalgebra of BH for some BH? So I need to make precise. So it's not really a subalgebra. So a C star algebra is some algebra, is an algebra which is isomorphic to a subalgebra of BH. Okay, so a C star algebra is nothing but, that means that it can be considered as a subalgebra of BH under some isomorphism. So there is a map from A to BH. So I should, so probably I should introduce. Okay, let me not define, I will just illustrate by, let me not give any more terminology. I will just say why CX is a subalgebra of BH, okay, and then you will know what I mean by saying subalgebra. So you look at, so CX is just a finite set. So let me mark them as 1 to n. And what is a function from x to c? It's just given by these numbers. So it's just given by an n tuple. It's just given by an n tuple A. Let me call it as A1, A2, An. Okay. So instead of thinking like this, and what is the multiplication? What is the addition? The addition is component wise, multiplication is component wise, and conjugation is taking complex conjugation component wise. So you can, instead of writing it like this, let me write it like this. Okay, so A is an element, F is a function, I'm calling it as by A. So this is an element in Cx. So take an element in Cx, an element in Cx is just an n tuple, and just put them as matrices. And this will give you a map from Cx to matrices. So Cx, this will give you a map from Cx to matrices, just putting it along the diagonal, and this will preserve all the structures which are involved. Is this linear? Yes, if you add two matrices, it's linear, it preserves the multiplication and it preserves the adjoint. So this is what I mean by saying, so through this map you can consider Cx as a subalgebra of Mn, and this is also injective, so everything is clear. So instead of considering A as an element of Cx, I can consider A as a matrix element when considered as a diagonal matrix. Okay. So this is what I mean by saying that Cx is a subalgebra of MNC. So why is CG? CG is also a subalgebra of some big matrix algebra, and the canonical representation is okay, maybe I should let me just say, so look at L2G, which is the basis element, which has basis elements marked by G, and take a group element CG, take A here and write A as summation AG delta G, and then define a map from CG to bounded operators on L2G by defining pi of A acting on EG is EH is AG delta G EH. So you just again to give a map from CG to here, it should be a linear map, and CG has a basis indexed by G's, delta G. So you just need to specify what happens on delta G's, and I just multiply them. Okay, so I'm rushing here a bit, so it's because I want to at least prove Gelfand-Naimark theorem. So it's a this will be a representation of CG. It will preserve all the structure, and so you can, and it will be injective. So you can consider CG as a subalgebra of bounded operators on L2G. Okay, so for me, okay, now I can state the theorem. So the theorem is this is the baby version. Okay, so as so if you have a C star algebra is just a subalgebra of BH. So let A subalgebra of BH be a unital star subalgebra. Okay. There are two. Okay, Gelfand-Naimark is this. So if A is commutative, then A is isomorphic to Cx for some finite set x. So what does isomorphism? So so you have a notion of star algebras, and then if you have two star algebras A and B, what it means to say A and B are isomorphic. So you have two star algebras, what it means to say A and B are isomorphic. If you have two vector spaces, what it means to say they are isomorphic, that means that there is a map from here to here and here to here, which preserves all the structures, addition, multiplication, star structure, and so on. Okay, the bottom arrow is not necessary. If you have a map from A to B, which is 1 1 and on 2, and you can take the bottom arrow to be the inverse map, which preserves all the structure. So you have, so what it means to say A and B are isomorphic. So you have a bijection between A and B. So as sets they are isomorphic, their cardinalities are the same. And this is not just a set, it has more structure. Whatever structure you are in, it should preserve it. So it should preserve addition, it should preserve scalar multiplication, it should preserve star structure. Then you say that A and B are isomorphic. Okay, so any commutative star subalgebra of BH is just isomorphic to Cx for some finite set x. Okay, so it is just functions on x. Okay, so the remaining, I think I will be able to convince you the proof. So let us start with a special case. Let us start with or M and C, whichever you prefer, and take a matrix which is self-adjoint. Okay, so if you have a self-adjoint matrix, or if you have a self-adjoint operator, have you studied spectral theorems? Spectral theorem for self-adjoint operators. I am seeing people have studied spectral theorem of self-adjoint operators. Okay, so let's do spectral theorem for self-adjoint operators and then we can come to this. Okay, so why did I bring that thing is the following. So if you take a single operator which is self-adjoint, that means that A equals A star, then you can create an algebra out of it, right? So how do I create an algebra out of it? It should be an algebra, so you take A square, A cube and so on, and then take the linear combinations of them. And so look at polynomials in A. Okay, so what I mean by this is all linear combinations of this. Okay, so if you multiply two polynomials, it's still going to be a polynomial. If you add two polynomials, it's still going to be a polynomial. Why it is closed under adjoint? Because A is A star, so the adjoint of A power k is also A power k. So this is closed under addition, multiplication and star structure. So this is a star subalgebra. Okay. And what does spectral theorem says? So spectral theorem says that so any answer, raise the hand and you can. Spectral theorem for self-adjoint operators, it's just finite dimensional spectral theorem. Okay, so have you studied that any self-adjoint operator can be diagonalized? Raise the hands for yes and no also raise. Only one yes. Okay, so the thing is any self-adjoint operator can be diagonalized. What do I mean by that? So if I take A in BH, which is self-adjoint, then okay, if I take a linear operator from H to H, you can always, once you choose a basis, you can always write that as a matrix, right? So once I choose a basis, you can always write A as a matrix. Blah 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 blah. So okay, this matrix depends on what basis that you choose. For every choice of basis, you have a matrix representation. Okay, but then how simple it can be for a what's that answer? So how simple it can be is that the simplest is the diagonal entries. So if you have a matrix with diagonal representation, if you can represent your operator as a diagonal matrix, then you can read out quite a lot of information about the operator. For example, the eigenvalues will be the diagonal elements and so on. So the point is that any self-adjoint matrix can be diagonalized. That is, you can choose a basis psi1, psi2, psi_n such that with respect to that basis, the matrix looks like this. But this is not just any basis, you can choose an orthonormal basis. So the spectral theorem says the following, that is, let A belongs to BH be self-adjoint, then there exists an orthonormal basis. There exists an orthonormal basis psi 1, psi 2, psi n and scalars lambda 1, lambda 2, lambda n such that a psi I is lambda I psi. Okay, so any self adjoint operator can be written as, so what is the matrix now corresponding to A? It is just the matrix corresponding to A is just the diagonal. The matrix of A corresponding to the basis psi 1, psi 2, psi n is just the diagonal lambda 1, lambda 2, lambda n. Okay, so how do we prove this? So I'll just give a sketch of a proof. So first you need to know that eigenvalues, you need to find eigenvalues and eigenvectors. Okay, you need to find n eigenvalues and n eigenvectors. That's it. So, but first you need to know whether there exists one eigenvalue. So will any operator on a finite dimensional space, will it have an eigenvalue? Yes. Okay. Suppose I consider this matrix. Okay, let me not discuss this. So any operator on a, we are dealing with complex matrices, right? So in any complex matrix we'll have an eigenvalue, but if we pose the same question in real, it's not necessary to have an eigenvalue. For example, this matrix, this is just if you think of them as matrix from R2 to R2, this sends the coordinates, it will send 0 1 to 1 0 to 0 1, which is E2, and it will send E2 0 1 to minus 1 0, which is minus E1. So geometrically it means that it sends the vector E1 to E2 and vector E2 to minus E1. So this is a rotation by 90 degree, and it can't have an eigenvalue, it can't have a real eigenvalue. Okay, so it can't have a real eigenvector, because if it has a real eigenvector, the line which correspond to that eigenvector has to be fixed by the operator A, and it is not possible because it rotates. Okay, but since we are dealing with the complex matrices, every complex matrix will have a complex eigenvalue. So let me take a complex eigenvalue and a complex eigenvector. So let me take, let lambda be an eigenvalue of A, with eigenvector psi. So what it means, it says that A psi is lambda psi, and now look at the orthogonal complement of psi. You can write psi as span of psi plus span of psi complement. Okay. So what is the action of A on span of psi? It is just multiplication by lambda. So it leaves this space invariant. Okay. Exercise, verify that A leaves the span of psi complement invariant, the orthogonal complement invariant. So you split H into one dimensional space and its complement, and so let me call it as W and W perp, and the equation A psi equal to lambda psi, where W is span psi. The equation A psi equals lambda psi tells you that A leaves W invariant, and now it's an exercise that prove that A leaves W perp invariant. So A sends W to W and A sends W perp to W perp. So A with this decomposition will look like lambda 0 and another operator A prime, where A prime is an operator on W. A prime is just A, but restricted to W perp. Okay, but W perp has dimension less than dimension of height, so you can apply induction to diagonalize A prime. Okay, so that's the proof of spectral theorem for self-adjoint operators. So any self-adjoint operator, it can be diagonalized. So you can find a orthonormal basis for which this happens. Okay. So the trick involved here is the fact that this is just proof by induction, and the fact that eigenvalues exist. So you can do let me reformulate this. So let me define the spectrum of A. This is called the spectrum of A, which is all the eigenvalues of A. Okay, and for every eigenvalue, collect all the eigenvectors, which is all those vectors psi, such that kernel of A such that A psi is lambda psi. And so what it says is that, so the spectral theorem says that you can write H as direct sum of sigma A H lambda. You can decompose your original Hilbert space, original finite dimensional product space, as a direct sum of H lambda. That's what it says, right? So this lambda i's might repeat, and then you collect them together. So you can you collect all those vectors for which A psi is lambda psi for a single lambda, and then add them up, you get your original space H. So this is a reformulation of the same statement that any self-adjoint operator can be diagonalized. And what is A on H lambda? A on H lambda is just lambda. Okay, so I think, I got sidetracked. So the trick involved here is that you can decompose H as a space W and its orthogonal complement, where both of them are invariant, and so you can apply induction and get the result. But a better thing one can do is the following, that is, maybe should I talk about projections? Yeah. So let me, so if I give you a subspace W in H, then you can always decompose H as W plus W perp. And so what is W perp? W perp is just all those etas for which psi eta is 0 for all psi in W. Okay. Now you can decompose H as W plus W perp, and with this decomposition define a new operator which is P from H to H, where P acting on psi is how should I write? So it is identity on W and 0 on W perp. So it's a linear operator. Any linear operator on H, any vector in H can be written as a vector in W plus a vector in W perp. So to give a linear operator on H, it is enough to define what happens on W and what happens on W perp, right? Because everything can be written as a linear combination of two things. So I am defining a linear operator from H to H. So call it PW from H to H by this equation. PW on W is identity and PW on W perp is 0. Okay, so if what is the full definition? It is that you take a vector psi in W and decompose it as W plus W perp, then P psi is just W. Okay, so if you have a subspace that comes with a corresponding decomposition, and this decomposition gives a linear operator from H to H, and what is the property of this linear operator is the following, that is, you verify that this satisfies this obvious relationship, and such an operator is called what we call it as projections. So this is just the orthogonal projection onto W. So you take psi and split it into a vector in W and W perp and project it to W. So that's the orthogonal projection of H onto W. And so every subspace corresponds to a orthogonal projection, and this is in fact a bijection. So so look at all subspaces. So what is a projection in BH? It is given by that equation. A projection is an operator P for which P square equals P equals P. Just remove the W. An operator P is called a projection if P square is P star. Okay, it's an idempotent and it is self-adjoint. So you have if you give a subspace, you have its orthogonal projection. And this association is actually bijective. That is, if you have so what is the reverse direction? If I give you a projection, what is the subspace that I will associate? Can anyone tell? So yeah, range of P, right? So because the range of P, it's orthogonal projection, it projects onto the range of W. Onto W, so it is just range of P. So this correspondence is actually bijective. So you can think of subspaces either, if you prefer, you can think of them as subspaces or you can think of them as projections. So what does spectral theorem says? Spectral theorem says that if you have a self-adjoint operator, then I can decompose my original space H as direct sum of H lambda. On each space H, it's lambda, right? So each H lambda is a subspace, and so it comes with an orthogonal projection. So let me call that orthogonal projection as P lambda. So okay, so this is a dictionary between subspaces and projection. So this is a bijection. So any subspace you can associate a projection, and so it's a bijection. And whatever you can say about subspaces, you can say in terms of projections. Okay, so I am going to reformulate everything in terms of projections. So whatever you can say about subspaces, you can say in terms of projections. So what it means to say two subspaces are orthogonal? We say W1 is orthogonal to W2 if all the inner products are orthogonal. This is a statement about subspaces, but here is a bijection between subspaces and projections. So there should be this statement should be can be translated in principle as a statement into projections, right? So it translates to, is there some, I was hearing some answers. Yeah, PW1, PW2 is 0. Okay, so orthogonality turns into the fact that their multiplication is 0. And what about this? That means they are all orthogonal and their sum adds up to W. And this will obviously, I mean, no, you have to verify, but this will turn into okay. So you can, the fact that you can, if you take a self-adjoint operator, you can decompose H as a direct sum of H lambda, where H lambda is called the eigenspace corresponding to the eigenvalue lambda. So this is in terms of subspaces, but I can, as I said here, I can translate everything in terms of subspaces to projections. Okay, so let us call let's call P lambda to be the projection corresponding to H lambda. Okay. Now what does this say? This says that summation P lambda is 1. Summation P lambda, so the direct sum of the projections corresponding to H lambda should add up to the projection corresponding to H. But H is a whole space, so the orthogonal projection corresponding to H is just the identity operator. So they all should add up to 1. And P lambda P mu should be 0 if lambda is not equal to mu. Okay, so this is just this decomposition. But there is one more thing, right? On P lambda, A is lambda. So what is A? Can you write A in terms of P lambdas? What is P lambda on H lambda? What is P lambda on H lambda? P lambda on H lambda is identity. What is P lambda on H mu if lambda is not equal to mu? I am hearing 0, right? So P lambda on H lambda is identity, but on everything else it's 0. So, but what is, so look at this. So I mean I'm going to give the answer. I'm not. So A can be written as summation lambda P lambda, where P lambdas are projections. And so what is this sum on H lambda? It's everything H mu, for example. Let me fix lambda naught. On H lambda naught, only the lambda corresponding to lambda naught will be identity, everything else is 0. So A on H lambda naught is lambda naught. Okay, so A is given by this. So another way of reformulating spectral theorem is the fact that any operator A can be written as a direct sum of projections as lambda times P lambda. Okay. Now let me prove I can't prove the full baby Gelfand-Neymark theorem. At least let me use this to prove for the example that we considered. So once you have this decomposition, I have a self-adjoint operator. Corresponding to this self-adjoint operator, I am associating an algebra. This is closed under addition, multiplication, and has star structure, blah blah blah. So, is this commutative? This is commutative, right? Because if you, this is commutative because it's generated by one element A, so it is commutative. It's a commutative star algebra. Okay. But what does this new thing say? That is, if I write A as A lambda P lambda, what is A square? Sorry, lambda P lambda. What is A square? You just expand it out. So you will end up getting lambda mu P lambda P mu. But P lambda P mu is 0 unless lambda equals mu. So, but then P lambda square is also P lambda. So this is equal to summation lambda square P lambda. Okay, so if A is summation lambda P lambda, A square is summation lambda square P lambda, and A cube is, you can guess it is summation lambda cube P lambda. Okay, so if I take a function f on okay, so I want to show that A is some C of some finite set, right? So let me show that A is just C of sigma A. So I mean this should tell you that to take powers of A, all I need to know is what happens to lambda square, lambda cube, and so on. It is just functions on lambda. So so let me give you a map from here to here. What is the map that I am going to give is the following. That is okay. So what is the basis? So to give a linear map from here to here, it's enough to know what happens on its basis, right? So what is the basis here? So for every element lambda in sigma A, look at delta lambda. Delta lambda is the one for which, except for lambda it's 0, on lambda it's lambda, on lambda it's 1. So it is the indicator function on lambda. So that will form a basis of sigma A. Let me send this to P lambda. Okay. So this will give you a map from here to here, and it's a very simple exercise to prove that this map is 1 1 and on 2. So with this map, A is just isomorphic to functions on the spectrum of A, and the spectrum of A means eigenvalues of A, and eigenvalues of A is a finite set, right? If you have a n cross n matrix, then there can be only n eigenvalues, at most n eigenvalues. Okay, but there is a catch here. Where is the catch? I am sending delta lambda to P lambda, and I am claiming that this is a 1 1 onto map onto A, and it preserves all the structure. So I will stop with this, but can someone explain where is the catch here? The catch is that you should first prove that P lambdas are actually in A. Right? What is A? A is just polynomials in here, but whereas P lambdas are projections onto these eigenspaces. So you should be able to express P lambda as a polynomial in A. Once you do that, then this map will give you a map from the spectrum of A to A, and this is the isomorphism. And so a singly generated star subalgebra is just the functions on a finite set. This is just a consequence of spectral theorem, and it's not very difficult to prove the baby version of spectral theorem, baby version of Gelfand-Naimark theorem from this. So I don't think I should. I have 5 minutes, but I don't want. Maybe I'll stop here. So, if you have a, so as I said, if you take a compact space, look at the continuous functions on X, and that will be a C star algebra, and any commutative C star algebra is isomorphic to Cx, where X is a compact Hausdorff space. C star algebra is a subalgebra of BH, where H is a Hilbert space and closed and so on. But okay, thank you.